Okay, so today we will start another new concept. And if you recall last two class, we discussed about multi-layer neural network, okay, and we call it artificial neural network. It's a multi-layer perceptron as a neural network. And what today we will learn, it's also under the neural network category, but it has some of its own features. We see CNN, okay. So there are, and then later on we will also learn RNN, okay. So there are different NN. So this CNN, so A means artificial, okay. And the C over here means convolution. So it's a convolution neural network. So it's still neural network, okay, but it has some of its special features. So let's take a look. And so machine learning previously, we already discussed quite a number of algorithms, is it? And feature, if you recall, feature plays very important role to the performance of machine learning algorithm, is it? And how we extract features, salient features here. Is it? Basically, there is also a field called feature engineering, is it? And previously, we also learned feature extraction, is it? And if you recall, we also learned the feature reduction. So anyway, so extract features basically plays important role, okay, in machine learning, okay. So, and then for neural network, based on what we previously also learned, is it, and it can learn feature from the raw data, okay, most useful for particular task. So like previously, particular task we learned like that MNIST, if you recall, that's for image recognition, okay. And it says, then it's common to consider neural network also as a feature extraction engine. Okay, so that's, later we will see. For CNN convolution neural network, it can achieve the goal for image processing, okay? How do we identify and extract? So here, there is an important concept, extract features. And basically here is the important features, is it? And if you recall, like regarding feature reduction, we previously learned like PCA, is it? And we can also choose important feature based on feature importance. Is it? So feature extraction, okay. And here says early layers, because for over here we consider it's regarding multi-layer. The multi-layer, so not a single layer, so multiple layer involved also with the hidden layers. So it says early layers, because if you recall, it's from left to right, is it? So after input layers, they can, here it says, extract some low-level features. What does this mean, low-level features? Okay, later on we will see with the image. Okay, image, okay. And so over here, the important concept, so let's just keep in mind, it's regarding extracting features, okay? Feature extraction, okay? So for multi-layer neural network, okay? And here, in particular, in some cases, not all the cases, okay? Deep convolutional neural network. So it can construct some feature hierarchy, okay? That's by combining low-level features in a layer-wise fashion to form higher layer-level features, okay? So anyway, so overall, here's the concept, what we needed to catch regarding convolutional neural network. It's regarding feature extraction, okay? So extract a feature. Okay, and then next, let's see. CNN, generally speaking, efficient for good at doing what kind of work, etc. So it normally do very well for image-related task. Okay, image-related. And why it is, later on we will also see when we take a closer look at the approach, okay. For image, be careful, okay, image. Image, the connectivity says it's a sparse connectivity. So the single element in the feature map is connected to only a small patch of pixels because it's regarding pixels. This, so like one pixel and the other pixels, generally speaking, is if you think about an image, etc. So normally you have some object here, and you also have some environment, etc. So it's pretty close to its small patches of pixels, kind of neighboring the pixels. So it's a sparse connected because generally speaking, in also in an image, a lot of times, etc. There are a lot of other pixels that's kind of unrelated to the target, etc. So that's why we see here is a keyword called sparse connectivity. Okay, and if you consider some other scenarios, they are close related with each other. And because of this, the image, that's why with image processing, we're using GPU, that you can also do parallel processing. Because like over here and this, not to have too strong connection. It doesn't matter if you just processing this corner or you just processing that corner simultaneously, etc. So that's a key feature. And the second one is regarding parameter sharing. Okay, it says same weights can be used for different patches of the input image. Later on, we will also see what does this mean, okay? So basically over here, it's some kind of filtering, okay? Then you can reuse the parameter. Okay, so this is why convolutional neural network is good at image processing, okay? And because of this reason, okay, it says the number of weights in the network can decrease dramatically, okay? And but we still see the ability to capture the important features. So over here, the next part, basically, I already explained. There's a nearby pixels more relevant to each other, than further away pixels, okay? So here are just some general concept. Okay, then what next? Let's see. So convolutional network. So anyway, so this is regarding multi-layer. Okay, so this multi-layer, then what kind of layer? Is it like previously when we discussed the neural network? So we see that the previous layer, each neuron connected with a neuron in the next layer. So we call this fully connected. Okay, fully connected. So that's the concept. But here we will see, okay, so those hidden layers, what are those hidden layers? So it includes one kind of layer, we call it a convolutional layer, so con layer. So a lot of time you will see that, okay. It's basic convolutional layer. And then we also have some, we call subsampling layer. We call it a pooling layer. So that's normally following convolutional layer. Okay, so convolutional layer then followed by pooling layer. Okay, following that, then you can do fully connected layer. So this F represents fully connected layer at the very end. And if you recall, previously we also learned the concept regarding dropout layer. And dropout layer, the purpose is to reduce overfitting. Okay, so the dropout layer, so sometimes we can also add them into the convolutional neural network, okay? And the fully connected layer, basically it's just multi-layer perceptron, okay? So that's the general layer information, okay? And also here, there is a point we needed to pay attention regarding the subsampling layer. So we call it a pooling layer, okay? And if you recall, regarding neural network, the goal is to find optimized weights. Is it? So over here, we have the weights connected one layer to the other layer. Is it? And we don't know. Is it? We want to find the optimal ones. Okay, so generally speaking, that's the goal. Is it? And we can use gradient descent. Is it? And basically for neural network, the key concept, let's recall as from input to output, is it sending samples and training weights? One step is we call feed forward neural network, is it? And then we adjust weights. We use back propagation. Back propagation. That's the concept. Okay. Okay, so anyway, so it's all involved, the weights. Then we adjust the weights. Is it? So convolution layer, pooling layer, fully connected layer, is it? Then regarding pooling layer, be careful as pooling layer don't have learnable parameters. Okay, so that means there is no weight or bias in pooling layer. Okay, then you may ask, then what do we do, etc. So later on we will see what does that mean. Okay, so keep this in mind. Okay, then the first, so when after you have input, normally the first step we do is we do convolution. So what is convolution? So basically here convolution can extract some feature. Okay, extract a feature. Okay, so here give us an example. So this is just some image, 6 by 6, 6 pixel by 6 pixel image. So each pixel you have a number, is it between 0 to 255? Is it a color scheme? Is it? So anyway, some number. So over here, the convolution means then you are going to apply some filter. Okay, we pick some filter. And over here, we pick this special matrix, 3 by 3 filter. And if you take a look, it has some special values. The first column or 1, second column or 0, third column or -1. It's kind of look like some vertical line, is it? If you visualize it, is it? Okay, so anyway, so this is the filtering. Then what you will do is, we said filter, is it? So what you are going to do is you are going to do patch by patch. So you apply this filter to the first patch of the original image. Okay, so what over here, we get this small patch, and we also write the value from the filter on the top. Then we are going to do the calculation. The calculation going to be conducted as you do element-wise multiplication. So it's element-wise. Multiplication. Okay, and then you sum them together. That's it. And we get some value. And then for this value, you are going to record it here. Okay, record it here. Okay, so that's the first one. Okay, and then we are going to keep doing this. Then you apply the filter to the next patch. So you shift a stride. And then you can define, suppose here we just define 1 pixel. You can also define each time you shift 2 pixel or you shift 3 pixel. That depends. Okay, assuming here we define shift 1 pixel, then you do the same thing. The element-wise multiplication and summation them together. Then we get this second value, we record it. Okay, and then you do the next patch. Okay, and after the next patch, then we can do the next patch. So that's how we come up with the first row value. Is it? Then the same thing, you can move on. Let's use this color. Then you can same thing, do vertical. Do vertical. Okay, then you can come up with this value. That's it. So after you apply to the whole image, then we can get this new we shouldn't call it, what can we call? Yeah, we can call it some kind of image also, okay? So anyway, we generated some new kind of matrix formatting, is it? But if you compare with the original, the size is smaller, is it? And the element, each element, the value is generated is because the filter applied to the original, is it using this rule? And then you generated these values, okay? So anyway, so this is called convolution. So convolution is you apply the filter patch by patch to the original image, and you slide the filter, that stride by stride, and then you generated a new matrix basically here, okay? So this is called convolution. And then next, let's see. And with that convolution that we just saw, that then the original 6 by 6 result in a 4 by 4. Is it? And the 4 by 4, but there are some disadvantages there. Is it? And one thing is the size of image shrink. And also pixels present in the corner of image. Okay, then you just apply them, just think about like this one. You just apply them once, basically. Basically just the first cell. Is it? Then you just use it once. But for the middle ones, because each time when you do the filtering, they will be covered a couple of times. Is it? So there are some of the corner that be dealt with fewer than the others. Is it? So that may, because sometimes you may have some important information on the edge of the image. Is it? Not necessarily everything is going to be in the middle. Is it? So how can we solve the problem? Is it? So that we can do padding. Okay, there is a concept called padding. Okay, so padding is you just expand. We manually add all of those like zeros. Is it? This is the original image, this part. And you manually expand the number of rows and the number of columns. Is it? We expand horizontally and vertically. Is it? Vertically, and get a larger matrix. Then we do convolution. Is it? Then we can keep the original size. And also all of the pixels, not just used by once or twice. Okay, so that's concept called padding. Okay, and here gave us more concept. Is it? So regarding the original one, is it? That's the original one. And then we do the padding. So basically we just add a bunch of zero, is it, around the original, is it? Then we do convolution so we can have some result, okay? And here assuming the stride is twice, is 2, is it? If you do 1, we should have another one, is it? But if you just do 2, then you can generate. And also here, the corner one, we also taken care of, is it, with some results. Okay, so that's regarding convolution and the padding. Okay, we know the concept. And previously, what we just discussed is about 2D, is it? But we will see a lot of time when we do convolution, it's over volume. Okay, over volume, so 3D. So what that means? Okay, so previously we just show a 2D image. 2D image. But a lot of times we can also have 3D image. Is it 3D image? So that's also possible. Is it? Assuming like if you have a video, and the video then is composed of number of frames. Is it? And each frame is a 2D image. Is it? But if you have a couple of them together, then you can kind of view it as 3D. Is it? So then in that case, how are we going to apply convolution on this kind of 3D image? So then in this case, the filter will also need to be 3D. Okay, so filter's dimension, the third dimension of a filter, okay, needed to be the same as the image. Okay, needed to be the same as the image. So, and then let's see the concept. So here we have 3D image. That we have width and height. And normally the third dimension represents some channel. Okay, some channel in the image. Okay, like a color channel, is a transparency channel, is it some kind of channel? Okay. So here the concept is a channel in the input and the filter should be the same. Is it? So here we have 3 images, 3D image. Then your filter should also be the same. But when you do the convolution, your result is going to be a 2D. Okay, so then what does that mean? So that means you apply the first filter to the first patch. Is it? The second filter to the second patch, the third one to the third patch. Is it? And then for that, we do element-wise multiplication. Is it? And then we do summation. So we generate a result. Is it? But over here, we have 3 of them. We have 3 of them. So then we need to also add all of them together. Is it? Then that goes to some result here. Okay, so that's how we deal with over volume. Okay. Okay, and over volume, but sometimes then the question is, can we also apply multiple filters? So what over here, what we mean is different filters. Is it different filters? Yes, of course. Like suppose this one is like 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1. Then this you can be 1, 1, 1, then 0, 0, 0, negative 1, negative 1, negative 1. This one is kind of vertical, the other is horizontal. Is it? Then in this case, then you need to have 2 different sets of filters. But for each set, you still do the same thing. Is it? Then with this one, it's kind of to identify vertical lines. That, and then in this case, to identify horizontal lines. So it's purely based on your filter. That then you can identify vertical lines and horizontal lines from your images. So basically, those are what? Those are features. Is it some low-level features that in your image? So then you can identify all sorts of features in your image when you apply different kind of filter. Okay, so here gave us the idea that convolution over a volume is that. So we know, like in image, there may involve vertical line and horizontal line. Like in this image, is that we clearly have vertical line and horizontal line. Is that then how do we detect those edges? Then we can use multiple filters. Is that so? One with vertical edge, and the other is a horizontal edge. So that's what we call the filter. So the filter can extract the specific feature that you need. That then for the image, that identify the vertical line and the horizontal line for us. So that's the neat part of the convolution. Okay, and then over here shows us convolution over volume. Is it? So this is the original input. Is it? So input image, and it's also three-dimensional. Is it? And over here we have 5 filters. Is it? So maybe you want to identify horizontal line, vertical line, horizontal line, maybe diagonal line. Is it? And maybe something else. Then for each of it, then suppose this is for vertical filter, and this is for horizontal filter, and this is for diagonal, this is for another diagonal, and then this is maybe for dot something. So then each filter is trying to identify a feature. The feature. Then so depends on what kind of feature you want to extract from the image. Is it? Then you can apply the filter that owns that kind of feature. So then you can convolute it. So that's why after you apply this kind of convolution, then your output, did you see it changed to the 3rd dimension? Now is 5. Is it your input, the 3rd one? Initially it's 3. Now it's changed to 5. Is it changed to 5? And then you can apply the pooling layer. Pooling layer later on we will explain. So that's that part of the concept. And then what next? Let's see the one layer of convolutional network. So it says, so we basically using filter, is it to convolve over the entire image? Is it then we can get the output? So after we do the same thing, if you recall previously for the net input. We are going also to add bias term, to the outcomes. And then we also apply some activation function. If you recall previously, that we learned like sigmoid can serve as activation function. The very first one we learned is stepwise. That activation function. Then in neural network, we also see this a lot. Is it linear, ReLU, rectified linear unit. Rectified linear unit. Is it? So if you draw, something looks like this. Is it? So it take whatever the value. Is it? So the maximum. So that's always going to be positive value. Is it either positive or zero? That's what this rectify mean. Okay. Apply to the activation function. Okay, so then it says this is called a convolution, one layer of convolution. Is it? So if we write it, so this is going to be net input. Is it? Then you apply the activation function to the net input. Okay, and once you have this A, is it? Once you have this A, then it's going to be input to the next layer. Okay, to the next layer. So this is the similar concept as what we learned in neural network. Okay, and what next try to show is some typical convolutional neural network. So over here it shows that. So initially we have 39 by 39 by 3. So you have 3 different channels. Is it? And here we apply 10 filters. Okay, 10 filters. And because of the 10 filter, and the filter size is 3 by 3. Is it? And this is a stride, so shifting unit. And here is a padding information. Okay, so after, because you have 10 filter, it's 3 by 3, so that's how this layer, hidden layer, then change it to 37 by 37 by 10. Is it? That's how this 10 comes from, because of the filtering. Okay, then next you said I'm going to want to extract more features. So then you can have 20 filter. Is it? And this is the size of the filter and the stride. Okay, that's how it comes up. The next one, change it to 20, the third dimension. Is it? And then based on that, you say, okay, I want to extract more features. Then you say 40 filter. That's how over here it comes up with 40 filters. But you can also see for each 2-dimensional, the size is decreasing after you apply the filter and the stride. Is it? And after that, so over here it's flattened. Is it? And we can also do polling. Is it? So that's the concept, general, typical convolutional neural network. Okay. So a typical ConvNet, basically there are 3 types of layer. Convolution layer, so you apply filtering. Okay, so this is filtering. So filtering means you can extract features. The features maybe you say, oh, I wanted to filter a person's face, etc. So if you have filter that can filter persons, then it will focus on that part. There's something like that. And then we also have pooling layer and the fully collected layer. Okay. Okay, so then we haven't discussed pooling layer. Okay, and if you recall, okay, pooling layer, not training parameters. Okay, so pooling layer don't train parameters. So then its purpose is to what? It's to reduce the size of inputs. Okay, reduce size of inputs. And then we can speed up the computation, because think about the image, that especially with high definition, that so there are a lot of pixels involved. So the computation, if we don't do something, it's going to be slow. So we want to speed up. So what is pooling layer? So regarding this one, the matrix, then after we apply pooling, so it's kind of, if you take a close look, so here we have kind of divided into 4 patch, is it? So within each patch, you pick the maximum value. The maximum value. So then you get this result. So this is called the max pooling. So for each patch, you find a maximum value. Okay. Then we get the pooling result. There are other kind of way you can do pooling. Okay. And here, this is also called a filter, that and based on the stride. Okay, so here stride means jump every 2 pixels. Okay, so for pooling, we can also do mean pooling. So depends. Okay, you can pick a different kind of pooling. Okay, and then next, let's see. So the convolution neural network, is it then plus pooling, how it works, is it? So previously, if you recall, we have 32 by 3, is it? Then over here, we apply the filter as 5, is it 5 layer, is it for the filter? Okay, so that's the convolution. Then what we can get is this result. So this is the first convolution. So after convolution, then we apply pooling. So normally, one convolution and one pooling together, we call it a layer in convolutional neural network. Okay, after that, then you can apply second time convolution and pooling. Okay, and then you can do flattening, is it? And over here, it's fully connected. So this is fully connected. Okay, so over here, it will give us a general ideas, okay. Okay, then what next one try to show us about multi-layer convolutional network, okay. So over here in this case, we have a 2D image. So the third dimension is just 1, okay. And then if you take a look, the filter size 5 by 5. This 32 is number of filters. Is it? So the third dimension. So we have 32. So that means from this image, you want to extract 32 different features. So you focus on, for each one, you focus on different feature from the original image. So that's how the result change to this. Is it? Then you apply pooling. Is it? So over here, it's basically just decrease the size. Is it? And then from here, you said, okay, I want to add more features. So 64, double the features. Is it? So that's how then it's generated with 64. then you decrease the size for each one, but then you have more features extracted out. That after that, then we can call flatten layer. That so you generated one dimension. As a one dimension, and then it's fully connected to the output, like suppose 10 digit or 10 image or something. That so this is fully connected. Okay, so over here we have convolution pooling. So basically this is layer 1, and then this is layer 2, something. That, and then you can do flatten and fully connected.
Dr. Liu?
And then